You know, it's kind of wild when you really stop and think about it. Have you ever wondered how massive applications, I'm talking Amazon, Netflix, or your favorite social media platform, how do they handle millions of users at the exact same time without completely crashing? It's honestly a fascinating engineering puzzle. So, in today's Explainer, we're going to explore the actual journey of scaling an application from absolute zero to millions of users. We're going to break down exactly how architects prevent their servers from just melting down under the pressure.
In our analysis today, we're unpacking 5 critical system design patterns that pretty much every back-end engineer eventually has to grapple with. We're going to look at the core problem statements, define these patterns, and see how they naturally evolve as the system grows.
Okay, let's dive right into this. Here is our structural roadmap for today. We've got 5 evolutionary steps of scaling a back-end system. First, monoliths versus microservices. Second, database per service. Third, the circuit breaker pattern. Fourth, event sourcing. And finally, scaling with CQRS. All right, number 1, monoliths versus microservices. We got to start right at the foundational level here. The absolute first decision you have to make when designing a system is choosing the core architecture of your hypothetical app.
And right away, we run into the classic debate. On one hand, you have the traditional monolith. It's basically a single, massive server holding your entire code base. Authentication, notifications, comments, they all just live completely crammed together. Now, it's super easy to manage at first, but here is the fatal flaw. If a bug in the notification system crashes, your entire server goes down, the whole shebang. On the flip side, we have microservices. This is where you break your backend into isolated, independent services. If the notification service crashes, no big deal. Your authentication and comments keep running perfectly fine. You get incredible isolation and the ability to scale each specific feature totally independently.
But, and this is a big but, as our source material constantly reminds us with this golden rule. In system design, everything comes with a trade-off. Breaking servers apart is amazing for preventing total system crashes, sure, but now you've introduced a massive new layer of complexity. You have to manage multiple different servers now, and more importantly, you have to figure out how they actually communicate and share data with each other over a network.
Which brings us to number 2, database per service. This highlights the absolute first major bottleneck you're going to hit in a microservices architecture.
Here's the brutal truth. Shared databases totally destroy true isolation. Seriously, imagine you split your app into all these beautiful microservices, but you're still using one single shared database for all of them. The notification service still has to reach into the shared users table to grab email addresses, but what if that notification service has a bug and accidentally deletes a bunch of user data? Well, you haven't really isolated your systems at all, have you? The database itself literally just becomes your single point of failure. So, what's the fix? It's the database per service architecture. Essentially, each independent microservice gets its own dedicated database, uniquely suited to its specific needs. It's about using the right tool for the exact right job. For example, the auth service might use MongoDB because, it needs a super flexible schema for user profiles. The notification service, maybe it uses ClickHouse because it needs to crunch heavy analytics like open rates. And the post service might rely on good old Postgres for strict relational data integrity. This setup gives you ultimate flexibility and, finally, true isolation. But remember that golden rule about trade-offs? Yeah, it's back. Because your data is now fractured across entirely different databases, you can no longer do simple database-level joins. If your post service needs user details, it can't just run a quick SQL join. Nope, it physically has to send a network request over to the auth service, grab the data, and then stitch it all together in the application code. This is what we call an application-level join. It definitely cranks up the complexity of your code, but honestly, it's just the price you pay for true independent scalability.
Let's move to number 3 and see how this builds into our next nightmare, the circuit breaker pattern. What exactly happens when these newly independent microservices rely on each other and one of them suddenly goes offline?
Well, it introduces a frankly terrifying scenario known as the cascade failure effect. Imagine service A requests data from service B and B needs data from service C. If service C goes down, service B just sits there, waiting and waiting for a response, eventually timing out and crashing. And because B crashed, well, now service A times out and crashes. It's literally a domino effect. Even though your services are technically separated, a failure deep down in a nested service can still ripple up and take down your entire system anyway.
To stop this bleeding, engineers use the circuit breaker pattern. Think of the actual electrical circuit breaker in your house. Instead of services talking directly to each other, they communicate through this smart proxy layer. It operates in 3 mechanical states. Step 1, it's closed, meaning data is flowing normally, everything's fine. But if the proxy detects the target service is failing, it instantly flips to step 2, open. It aggressively blocks all requests right at the door, preventing the dependent services from waiting around and crashing. It fails fast. Then, after a set amount of time, it shifts into step 3, half open. It basically lets just a tiny trickle of traffic through to test the waters and see if the service has recovered. If it has, it closes the circuit again. It's such an incredibly elegant way to protect the system from cascading meltdowns.
All right, number 4, event sourcing. Let's really scale things up now. We're talking high-throughput systems, Amazon on Black Friday, or global banking networks. At this level of scale, rapid, simultaneous database writes cause massive lock bottlenecks. To actually survive this, we require a massive paradigm shift in how we think about data. The rule here is simple. Stop mutating state and start logging immutable events. Traditionally, right, if an order status changes, you go in and update that specific row in your database from placed to shipped. But constantly overwriting the same piece of data requires database locks, and that brings everything to a grinding halt when millions of requests are hitting at the exact same second. And this brilliantly illustrates the event sourcing alternative. Instead of overwriting a single current state, you maintain an immutable chronological stream of events. At 12 p.m., you append a log saying order placed. You never, ever delete or change that log. At 12:10 p.m., you just append a brand new log, ready to ship. At 12:30 p.m., you append shipping. You're just constantly adding to the end of a continuous log. The benefits here are absolutely immense. It completely eliminates those nasty database locks because you're only ever appending new data. You're never fighting to update old data. This event stream just becomes your ultimate undeniable source of truth. If a user asks for their current order status, the system just quickly reads the logs and hands them the latest one. Actually, this is exactly how banking ledgers work. Your bank doesn't just store one single isolated number for your balance. No way. It stores a continuous historical log of every single plus and minus transaction. To get your current balance, it literally just calculates the sum of that history. Which brings us to number 5, scaling with CQRS. Because, as you might have guessed, we have one final bottleneck to address. At a massive scale, even with event sourcing, writing all of these countless events to the database is still going to slow down the read requests from normal users who just want to casually view their profile data. This is where we introduce CQRS. It stands for Command Query Responsibility Segregation. I know it sounds super intimidating, but it basically just means we are splitting our read operations and our write operations into 2 completely separate systems. And it builds perfectly on top of that event sourcing stream we just talked about.
Now, what's really interesting about this setup is how distinctly these 2 sides operate. You've got the command side, which handles all your heavy lifting and mutations, creates, updates, deletes. It takes user actions and appends them straight to your event stream. But here's the kicker. Users don't actually read from that stream. Instead, quietly in the background, the system takes those events and updates a completely separate query-side database. This query database is heavily denormalized. It's optimized purely for blindingly fast reading. So when a user wants to view their profile, they fetch it instantly from the query side, without ever touching or slowing down the super busy command side.
But coming all the way back around to our golden rule, there is one final trade-off for achieving this level of massive global scale, and that is eventual consistency. Because the command side has to process the event and then update the query side in the background, there is a tiny delay. The read data might be milliseconds or sometimes even seconds behind the write data. You're effectively trading perfect, instant consistency for the superpower to scale infinitely without bottlenecking. And that, my friends, brings us to the end of our architectural journey today. From ripping apart a monolith to wrangling isolated databases, protecting them with circuit breakers, and eventually splitting reads and writes entirely, it all comes down to the compromises you're willing to make as an engineer. So, I'll leave you with this question to ponder for your own projects. Are you ready to trade consistency for scale in your next build? Thanks so much for joining me on this explainer, and as always, keep building.